Okay, we're continuing with the study of linear approximations of two variables. I wanted to give you the third version of this, which is more like what the main text has, which is that you kind of put this all into one thing, and you make it so that you're talking about one thing going to 0. What we want is that the error in this approximation, here's delta z, here's the actual change between the value of f at some nearby point xy and the value at the base point. And here's the approximation as if you follow the tangent plane across. I want the difference of those to be small. And so the main text says you take delta z minus dz, basically. It doesn't use that notation. But here's what that ends up doing. It says take f of x y minus f of x naught y naught. And I know my x's look like y, sorry. And so that's the actual change. Then you subtract off what you think your prediction for the change was, which was I'll put that in parentheses. Okay. So that is the difference between the actual change and the predicted change in the function. And the way the handout says, basically, is it's that stuff. And another way to say basically exactly what the handout is saying is if you take that and you divide it by the magnitude of the vector delta x comma delta y, then you should get something that's going to 0. So we're going to take magnitude of the vector delta x comma delta y. And that should go to 0 as delta x and delta y go to 0. And I don't want to get into the details of which is a better definition or whatever. They're both good. But it's all about comparing these two guys and saying that they really should be a good approximation. And in particular, let's go back to the subtleties about limits. Remember, the subtleties here is that this can go in any direction. No matter what direction you go in, no matter which point, how I start at the base point and I go out in any kind of direction in x and y, the tangent plane is supposed to be giving me a reasonably good approximation, actually quite a good approximation for what the function is doing. And we saw some examples of functions where it works along the coordinate directions because the partial derivatives are right, but it doesn't work in other directions. Now, let me give you just a fourth version of this. If you look in the main text that we're using, it doesn't mention fx and fy in the definition of differentiability. And it's got very much a mathematician's definition. It says, if you just manage to give me any number, a and b, say, that makes this work, then I'm going to accept that as a linear approximation. And if you say, oh no, I'm not going to call it f sub x, the partial derivative, f sub y, the partial derivative, you just say that the linear approximation, or their version, is the tangent approximation, is like a delta x plus b delta y. And if that works, and if it satisfies this definition, then say, run with it. That's a good tangent approximation. How could it be bad if it has this wonderful property that the error between that and the actual change in z is really, really small? And then, of course, they prove a theorem right off the bat, right after that. And I don't need you to read and understand the proof of that theorem. But there is a theorem that says, well, you can't actually fake it. If you pick an a and b that actually work for that, they actually have to be the partial derivatives. Okay? So, and mathematicians love that, of not having to assume right off the bat that there's a formula for something. Make a very general definition that appears to work for a lot of different possibilities, and then show that you're actually forced to use these particular things as possibilities. It really makes it more general and more elegant, but it makes it more general. That nobody can come along and say, oh, I have a different definition of that. You were just being too simplistic in using the partial derivatives. I'm going to use a different a and b. And then the theorem says, no, you can't. Even if you tried to, you'd have to use the partial derivatives. And then, of course, there's even a fifth version. These are all really the same thing. I hope it's not too confusing to have so many terminology. And I mentioned this in class the other day, is that everything here really deserves to be vectors. The x and the y are paired together. And if you say x is the vector whose components are x and y, and delta x, the vector, is delta x delta y, or in other words, it's the vector difference between my vector point and my vector base point, then this in particular is very interesting, that this combination, or this combination here, of coefficient delta x, coefficient delta y, that seems like it's a dot product. And we're just going to say vector A is A and B. Then what we're looking at is a nice vector interpretation of the linear approximation, or the tangent approximation. It's start at your base point value, as always, and then just add this vector A dot with delta x. That's very elegant. That to figure out how much you go up or down, and again, in this one of the nice notations for this is dz. This is the idealized amount of change in the z variable. dz, I'll remind you another place we saw that. That idealized amount of change in the x variable, or in the z variable, the output of the function, is a coefficient times delta x plus a coefficient times delta y. And you can interpret that as a dot product. And again, you could think, oh, as long as I can find some cool vector A that has that property, that gives me the right approximation, that's great. Well, we've already seen that we must, for this to work, we must use A to be the vector whose components are given by the partial derivatives. Or if you like, fx, I'm going to drop the x naught, y naught just to save a little time and space. If you like ij notation, it's that. And there's in fact a very fancy, or a very nice notation for that. And I know this is a really notation-heavy lecture here, but we have to be prepared for it. And we say the gradient of f, evaluated at x naught, y naught, is exactly this vector. It's a vector sitting at that point which encodes both partial derivatives, and more important, by this equation, it encodes all of the linear approximations you could possibly want to do in any direction of that function. And I'm going to put a vector there. Some people would put a vector sign, some people don't. So for example, remember our example? We kind of went away from our example here. It was where z equals y ln x at 1, 4. We found that fx at 1, 4 was 4, fy at 1, 4 was 0. And a very cool way to summarize that is that the gradient vector at, the gradient vector at that point is just exactly 4I plus 0j, or 4, 0. And the tangent approximation in this cool vector language is just f of 1, 4 plus the vector 4, 0 dotted with the delta x vector. And this happened to be 0. And because that's a 0, that simplifies. It, again, is just 4 times just the delta x part, or 4 times x minus 1. It's the same formula, but just with a new interpretation. Okay, so the gradient is going to be a very cool object. What we're going to do soon is we're not going to just look at the gradient at a single point, because we can do this at any point. We can pick a new x naught, y naught, not just 1, 4, and we're going to get a vector at every single point in space. And those vectors describe the first derivative, the first order rates of change of my function at any given point in space. And we're going to have some very cool geometric interpretation for that. But right now, we're just going to play with these different ideas of using linear approximations and get familiar with some of the notation for linear approximations. Okay, that's a good place to stop.